Okay, since I had a bunch of people ask quite a bit about number 50 here, I thought maybe I better just make a video solution and send that out to everybody. So chapter number 28, number 50, is a good one, both mathematically and conceptually here. So I'm gonna give this a try here. If you've got a chance to already do it, great. This still might be useful here. I might approach it a little different. In fact, I want to do two different approaches here. But it says, determine the equilibrium charge on the capacitor in the circuit as a function of R. Okay, now the circuit itself looks something like this. It has a battery of 5 volts, and the current would come out of the battery, and then it splits. And so first split would go to a 3 ohm resistor, and the right side of the split would go to a 2 ohm resistor. Then, depending if the capacitor is charged or not, there would be flowing through this branch and charging up the capacitor. But one of the first key understandings here is it says the equilibrium charge. So eventually, and I say eventually, but it's really going to be a short amount of time, as we probably calculated, if you remember doing one like this in 31, where the time constant, it was, I forget the number, but it was, in the millionths of a second. So it won't take long. So after a small fraction of a second, we're going to reach equilibrium. And so that's kind of that phrase there that they say out of an equilibrium charge. And it's also kind of a key step to this problem, as well as number 31, is to recognize that after a long period of time, which, like I said, could just be, 10 millionths of a second, you would have then right here no current flowing through. And so if you essentially just, in your mind for a second, imagine the capacitor not there and call this then the voltage at point A. So I'll give this point A, and then here will be the voltage at point B. You could go ahead then and say something like this, that for the capacitor, take the capacitance, it would be the charge on the capacitor divided by the voltage between A and B. Okay, and that's really kind of what this part A, and there's a lot of parts to this, is saying here. It says, what is the charge? So the charge would be the capacitor times the voltage between A and B. And I'll just do absolute value, because as you'll see, whether A is bigger than B would be very dependent on the value of R. So it may be A is lower than B until you'll get positive charges on this side of the capacitor, which would make negatives on the right-hand side. Or it could be the other way around. I won't draw that, but we really are leaving that as an option, which way the capacitor is actually charged. So this key problem, really a lot like 31, is to figure out what is the voltage at A and the voltage at B. And so maybe the thing to do is to do a loop. If I called, let's see, AB, if I called this maybe C and this point D, and I did a loop that started at D, went around to C, then through B, and then finished back to D, that would look something like this. So from D to C, I would increase with 5 volts. Once I got here to C, then there would be a decrease in voltage, and I probably should put a label here, call this current number 1 going off to the left, and current number 2 going off to the right. And so it would be a resistance of 3 times a current of 1. And then we would get to this point B. Knowing none of the current goes through the capacitor after a long period of time, it would then have to go the same amount of current through the 80 ohm resistor back to point D. And it should be these 3 elements, the battery and the 3 ohm resistor and the 80 ohm resistor. And the sum of all those around a loop would be 0. And so if we do a little mathematics here, I guess we would leave a 5 on this side. That would make 83. Bring it back over, and we got 5 over 83. Changing that into a decimal, 5 divided by 83 is 0.0602 amps, or if you want, 60.2 milliamps. So there's the current in equilibrium going down the left-hand side. And notice that had nothing to do with R. And so this current's going to stay the same no matter what they ask throughout this problem about R. So this will be the first of many times I'll probably say this. You know, be careful and that you are doing more than just doing the math. You're reading the math. And so this loop remains unchanged no matter what I do with R. Which means I can look at the other loop. And so the other loop, which again, if I start at D and go to C, but this time go to the right-hand side and go to A and then back to D, it would look something like this. Again, it would be 5 volts. Then it would be minus 2I2. And then another minus, and same logic, if I2 is right here and gets to point A and the capacitor is now full, nothing will go that way, so the same current, I2, must head on down through the resistor, which we don't know its value, we're just going to label it as R. And so coming up with the same logic here, current number 2, if we group these together and move them over and then divide, would be 2 plus R. And so there's the current in the two sides, the left-hand side and the right-hand side. And of course, depends upon that value of R. Okay, so the reason I did all that is because I really want to find, coming back to the main part of this problem, the voltage difference. So I need to find the voltage at B and also the voltage at A and subtract the two. Okay, so voltage at B is probably the easier one because if you take this as the lower part of the battery, this would be the increase. So this would just be currents of I1 times the 80 ohms. And as we said earlier, this is 0.0602 amps for the current in number 1, and then times the 80. So again, keep in mind that not only do we have a number, but that number is going to be the same. So I've already got the current. I'll just hit times 80, and this will give me a voltage of 4.82, okay? Now, maybe this might be a good time to point out as you're doing this really part is what we'd call a voltage divider because, again, the whole thing is 5 volts, and you lose a little bit, and then you lose the rest. So point B has to be somewhere between 0 and 5, depending on the value of the resistors. And, of course, since they have the same current, the most change would be with the higher resistor. So we have a 3 and an 80. Obviously, 80 is a lot more than the 3. So just conceptually, or what I might, again, say, reading all this math, is I would have just looked at this right away, and I know that this voltage at B is between 0 and 5 for sure, because it's dividing the voltage. It's someplace between them. This would be at 5, and this would be at 0. But I would also know right away that it is really, really close to the 5, because most of it's going to be here, because the same current times 80 is going to be a lot bigger number than the same current times 3. And so sure enough, I get a voltage of 4.82 here for that voltage, which is at point B. Now point A is kind of the variable one. Point A is, again, current number 2, and same logic. It'd be current number 2 times this resistor, which, again, we don't know the resistance, and we don't know then even what the current is, because that depends upon that resistance. So that would just make the 5R over 2 plus R really kind of the best we can do at that point. And so hanging on to those and then answering this question, what is the charge on the capacitor as a function of R, which brings us back to here, is I'd put in the capacitance. And so, I don't think I put it in my diagram, but my diagram, I gotta find my diagram again, was 3, let me put it here, 3 microfarads. And so that's the capacitance. All right, so putting it into that equation, and I always forget how this red pen, I like how it stands out on the video, but it also bleeds through. Let me put a piece of paper under there. And so this would be the 3 microfarad. And then the voltage difference would be the 4.8, that's a terrible 8, 82 from B minus the 5R over 2 plus R. And I guess technically I better do absolute value, because as you can begin to see that for most of the values of R, probably this R is going to give a value, you know, like certainly if this is like 2, this would divide it directly in half, and the voltage at A would be lower than B, because remember B has got an 80 in here, and so it's depending on this value, A is going to be above or below this 4.82. So we can have R values really, really high, and so we'd be above it, but most of them, I think, I would say most of them, I mean, it's an infinite number between 0 and 5, but I'd say for the most part, we would be, voltage at A would be lower than B. So I'll write it in this fashion, but we don't really know. And so there would be the equation. And in fact, I think I'm done here. It said write out the equation. I guess I could do a distributive property if you want. I could do and maybe I should, the 3, and I'll leave the micro as a unit here, so it would be 3 times the 4.82, and so that's going to be 14.46 minus, and the 3 times the 5 is 15R over 2 plus R, and that would be in micro, and then this would be coulombs, because that's a Faraday, and then that's in volts. And so remember, a Faraday is a, Faraday is a, just drawing a blank here, must be a charge, a coulomb per volt, and then multiplied by volts, we get the coulombs. All right. So, and I suppose absolute value would be appropriate there. Three times 5, yeah, that looks good, but I'm just kind of scanning the author's solution. And why does the author have $28? Oh, I see what the author did. Okay, so then the author does one more step. The author puts it over a common denominator of 2 plus R. Okay. And so that means this 14.46 would have to be a 2 plus an R to get it to the same denominator minus a 15R. And, okay, so that is probably where that number comes from. Double 2, yeah, 28. So this is 28.92. And then we would have the, here we would have the 14.46, and we would subtract then a 15, giving me a negative 0.54R all over 2R. And so that's what we get for a common denominator. Let me just look at your author's solution. Yeah, that's what he has. Okay, so if we want it in that form or that form, whichever is the kind of the most convenient, page 2 here, this is really the answer to part A. All right, let me come back to the question and keep reading it. Okay, so says B, evaluate the charge when R equals to 10. Okay. That's just a straight kind of plug it in and see what I get. Maybe the easiest thing is just to do the math, not really read the math, but I'm going to kind of pause on that. So this would be the 28.92 minus, and so if R is going to be, let me come back, what I say, 10. 10 times this would be 5.4, and then R, whoops, I forgot the little plus sign in here. And then 10 plus 2 would be 12. And so this would be a 28.92 minus 5.4, and divide that by 12, and I would get 1.98 microcoulombs if I just kind of do a direct, plug and chug in there. But this might be a good point to, also realize, coming back to here, that if they tell us, it is a 10, even without coming back to these equations, maybe we could come over here and realize that the current then is going to be 5 divided by, and it would all be in a series here. So this would be divided by 12. So that's how much current we would have here. And then the voltage at A would be that current times that resistance. And so this would be the voltage at A, 4.166. So in some sense, I might say, you know what? As we said earlier, B would be 4.82 no matter what I do to R. And then point A, I just argued that it would, and I'll just round it to be this voltage. So if I take this number and subtract the 4.82, not worrying about the minus sign here, that's the voltage. And if I multiply then that by the 3 microcoulombs, there it is, the 1.96. So I don't know if you want to call that more reading the math or doing the math. It was a lot doing the math, but it was also a little bit of reading the math, kind of going back to just the fundamental that, that'd be easy to calculate the current. It would just be 5 volts divided by 12, sure. And then once I have that, I multiply by 10, that's the voltage. And then just take the difference between those two and then multiply by the capacitance. And so that was my kind of quick and dirty way of maybe following more of the physics than the math. But either way, hopefully you see both. And like I said, since you've just done A, probably that's your natural reaction, is just kind of do, a plug and chug here. Now, I did the formula. And I think you'll see that in all these. Look, question C says, can the charge on the capacitor be 0? And again, maybe I'll start with the physics on this one before I kind of go back to the math, because obviously you could just set this equation in A equal to 0 and solve for R, and I will do that. But in this case, I think actually looking just at the fundamental physics would be a little bit quicker and make more sense. I would just say, look, here, instead of coming back here and doing the math, I'm just going to look here and say, well, yeah, there's going to be 0 charge if these voltages are the same. And we already know B was a voltage of 4.82. So that would just tell me then if the voltage at A is 4.28, that's what I would get. Now, it would take a little bit of, I'll call it reverse engineering going back here, because that number then is actually made up a little bit of the current and the resistance. And so the current, as we said, would have to be 5 divided by this 2 plus R, and then times R. And I don't know if that's easier to solve this and set it equal to 0. But let's, do both. So I'll hold off on solving this for a second, because if I were just doing, say, the math, I probably would just do this, 28.29 minus 0.54 R divided by 2 plus R would be 0. And so I would just solve that. And hopefully I get the same thing. I think you could even see it here in this step. If I go 2 times this, let's see, what is this? 4.82 times a 2, if I bring this over, would be 9.64. and then plus 4.82. Let's see, 4.82 times R, and then 5R. And so 9.64 would be this 5 minus 4.82, and that's 0.18 R. And so taking the, oh, maybe I should put the calculator in the screen here, but taking that 9.64 and divided by the 0.18, I get an R of about a 53.6 ohms. And I hope I kind of get the same thing here. In fact, this math would be pretty easy, so maybe I should have just done the math, because you multiply it by that and that goes away. And so this will become a 28.92 equals 0.54 R. And so R is 28.92 divided by 0.54. And sure enough, it's 53.6 also. So I guess this, just doing the math, would have been a much easier process than pointing out that the voltage at A would have been this number, and then we've got, top and bottom, and so we've got to cross multiply and distribute and solve. So you can decide which is better. But I like this because I'm thinking about the physics, and although I like this too because this is just pretty easy, just set equal to 0 and complete. So whatever works, but definitely yeah, that's would be the appropriate resistance here. I think that was as C. Can the charge on the capacitor be 0? So yes. Oh, and if so, what is the value of R? Yeah, so I just solved that. I didn't read far enough, but I'm glad I did that. And then D, what is the maximum possible magnitude of the charge on the capacitor? And for what value of R is this achieved? Now, again, we can do this by both the math, just do the math, or we can read the math. And I think in this case, reading the math is a lot easier, I think. I thought that before, and it didn't come out that way. So let me try D here on page 3. And when I come back to this picture, remember that we already argued that point B earlier on, where was it, back here, is going to be locked in at a voltage of 4.82. This is the voltage divider. And over here, A is essentially a voltage divider. But where it divides, how much it is, depends on that value of R. That's where this equation came from. And so as we argued over here on the left-hand side, since the same current goes down here, if, say, these two resistors were the same, this middle point would exactly split it right in the middle, and so that would be 2.5 volts. Now, that's not what we have. We have a resistance here that's much greater. So the current times 80 here, so the change in energy here is much bigger than the current times the 3. That's why we said the voltage at B would be much, much, much greater, or the step from B to D would be much greater than the step from C to B. That's why B is going to be really, really close to 5. And sure enough, it was 4.82. So I could make the same argument here that R, I can pick it in such a way that voltage at A can be anywhere from somewhere close to the voltage down here at 0 to something very high and very close to the value at 5. And I get the most charge when the voltage between these differ the most. So that would just tell me conceptually that this is already at 4.82. If I made R really, really big, this is going to make this voltage very, very close to 5. And in fact, if I made this infinitely big, you would say it is at 5. And so the difference between 5 and the voltage at B would only be 0.18. That is not much of a voltage change. I can get a much greater voltage change if the voltage at A is lower, sort of near 0. In fact, maybe all the way to 0. Because if I can make the voltage at A further and further away from the voltage that is set at B, I would get more voltage and therefore more charge. So that just tells me, from just kind of looking at the physics of this, that I would really get the most charge when the voltage at A is 0. Because then I would have a difference of 4.82 for the voltage at B minus the voltage at A, which would be 0. And when would I get a voltage of 0? Well, when there's no resistance, right? Coming back here, the voltage at A is when resistance is, current times the resistance. And if there's no resistance, or if they want us to put something, then okay, very, 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 very small value, I will be very close to 0. So I would answer this one by saying I'm going to get the most charge when the voltage difference, so this is 3 microfarads, is 4.82. That's going to be the charge, and that's going to occur when the resistance is 0. And now I can't remember if they asked for how much charge or if they asked for what the resistance would be. But I'm going to do both here, 3 times 4.82, and come up with 14.46 microcoulombs. All right. So let me come back to the question. The question in D said, what is the maximum possible magnitude of the charge on the capacitor? So there it is. Oh, they didn't ask for both. And for what value of R is this achieved? Now, just for completeness, since I did this, what I'd say more by physics than by math, let me also do it by math. Because we had way back in A this nice little equation that said, what is the charge on the capacitor? And when I hear somebody talk about maximums, to me that sounds like calculus, and that means take the derivative. But let me also be careful, maybe a little calculus review here. If you have a function that maybe does this, and these are the boundaries that you can have. If you take its derivative and set it equal to 0, 0 gives you maximums, local, and minimums, local. So if we set it equal to 0, we have to then double check to see if it's a maximum or a minimum. But also, I'm hoping you're seeing in this graph, the other thing we have to be careful for is the boundary could actually be higher. Their derivative is not equal to 0. Of course, another thing, and I don't think we have that problem here, is functions that look like this. They have a cuspid. And so the derivative is 0 here, the derivative is 0 here, the boundary is here, the boundary is here. And then here we have some place where the derivative is undefined, and that could actually be on the maximum of the function. So that's why in your math class you learned that there are 3 places you want to hunt for maximums or minimums. And that is, when is the derivative equal to 0? And then don't forget the boundaries, and don't forget places where the derivative would be undefined. So if we wanted to do this more mathematical in nature, we might come over here and maybe even graph it at first. If you plotted R on the horizontal axis and then this Q on the vertical axis, you can kind of see in this equation that in the beginning part here, when R is really small, something maybe much less than 2, you can just kind of ignore that for a second and you get a line. And so this would be this 28.9 divided by 2, really. So you would have an intercept of about 14.46. And then it would have a negative slope. And so it would begin something like that. But for really large values of R, then you can kind of ignore the 2 up here, and then the R's would cancel off here, and you, really large values of R, this would be so big you can kind of ignore that. And then you would just have that cancel off, and so it would be a negative 0.56, and so it would be something kind of on the bottom maybe I'll put a kind of a transitional space here, but for large values of r, it would follow that hyperbola effect. And so it looks like there'd be some kind of transition that wouldn't be quite a straight line as my drawing shows, but kind of a transition. So if I was just drawing this, I would say there are no places where I have a slope equal to 0. I'm just going to have the boundaries. And then, of course, that would tell me the boundary would be when right here, that's where it's its maximum, and so that's when r equals to 0. And then once I know r is equal to 0, I could put that in there and put r equal to 0. That one goes away, that one goes away, and I just have 28.92 divided by 2, which is where I got that number, 14.46, which, of course, is the same thing we got when we did it just from the physical conceptual view of it. And maybe I won't take the time, but you can, if you want, take the derivative and set it equal to 0, and you'll see there is no place where that is a solution. And there's no cuspids. There's no ill-defined place, too. So that would be a lot of math here. And so I'd kind of stay away from that. And definitely the physics, I think, is a better option there. But I'll throw that out there as a nice way of doing it. In fact, now that I did it, let me kind of look at your author. What did he say? Yeah, 14.5 microcoulombs is the charge when r equals to 0. And I believe there's one last part to this, part E. Okay, so part E says, is the experimental meaningful to take r equal infinity? Explain your answer. If so, what charge magnitude does this imply? And then they got a suggestion here to do part B before A. Okay, well, I didn't do that. But here it says, taking R equaling infinity. Oh, and by the way, my graph could have been misleading because I was drawing this out to infinity. That was the other boundary. But I put an actual physical boundary in there. But the R could go from 0 out to infinity. And R infinity experimentally would really just mean that just completely remove the resistor. I mean, back to our circuit, it would be, say, just take that out. So your circuit, I guess, would look like this. You would have your 5 volts. You would have this coming through the 3 ohm, splitting off again to the 80 ohm, and this other resistor would be useful only initially when it was charging up the capacitor. And once the capacitor charged up, there would be no current going this direction. And so there would be no IR here. There would be no current. And so there'd be no change. And so this point is already at 5 volts. So the voltage at A would be this 5 volts. That's what I was saying back kind of here in the first part. If, again, you let R get really, really, really big, you can kind of ignore this too mathematically. You have R divided by R, and you just get up with a 5. So you get 5 if R approaches infinity. And of course, then that means the voltage difference would be this 5 volts minus what we already said, voltage B doesn't change. That was at 4.82. That's what I was saying earlier. This would come out to be a 0.18. That's the voltage difference. And so to get the charge, you would just take the capacitance times that voltage difference, which again is that 3 micro. And 3 times 18 is the 54. And so this would be 50.54 microcoulombs for the charge in a scenario like this. We'd actually charge this up to just a small amount, and then the current would stop flowing. But the current would keep continuing to go through this part B of the loop. But like I said, once you have an infinite amount, you would get that. Now, of course, you could have done all of this just way back here, and then again, more of the math. Just take the limit as r goes to infinity. Which again, if r goes to infinity, that's small compared to that. So okay, ignore that. And also, when r goes to infinity, plus 2 doesn't really matter, so ignore that. So you have 0.54r over r, and then the r's cancel, and so you have 0.54, and sure enough, that's what I have. Now, technically negative, I switched the order because, again, this is where this would be higher, so this would be positive, this would be negative. That's why I said, depending on how you want to do this, this would be absolute value. And so, what does it say here? Explain your answer, and if so, what charge and magnitude does this imply? And so I think the author really wants to say that it would be there'd be a charge, it would be that 0.54 microcoulombs, and it would be kind of the reverse of what we had before. Hope that helps. Bye now.